Hello everyone. We'll do a very brief summary of particle kinematics in this particular concept talk. Okay, I'm going to consider a particle traveling along an arbitrary path. Okay, so here is the path of this particle. Let's say that the particle is traveling from the top to the bottom to the top. Okay, first thing is I'm going to consider a point in time here. Okay, so that let's say that this is the point in time that I'm interested. Okay, I'm going to set up a fixed frame which is going to observe the motion of this particle at that instant in time. Okay, so here is that fixed frame. Let me make sure these are all joined together. And then what I'm going to do is I'm going to draw an osculating circle or a tangent circle at that particular point on the path. Okay, so look at this. So I'm going to draw that big circle. Okay, and I'm going to make sure that it's tangent to the path. Okay, so this is going to be my tangent circle. Okay, I'm sorry, sometimes it doesn't let me do things that I want to do, like other things in life. This is the local tangent circle or osculating circle. And let me say that the center of this circle is located probably somewhere approximately here. Let me call that center as C. Okay, the center of this circle is C. Okay, and I do need the osculating circle. Why do I need the osculating circle? Is so that I can specify what my normal direction is and my tangential direction is. Okay, all right, so with this said, I'm going to start off by drawing the position vector from the fixed observer who is sitting here. Okay, this is the direction of the position vector. Okay, this I'm going to call as r of t. And once I have the position vector, then I can draw the radial transverse unit vectors. So here is the radial unit vector. Okay, so this is going to be r of er, I'm sorry. And then I'm going to have the transverse unit vector, which is e theta right there, which is perpendicular to er. And I drew it in this direction because I'm assuming this to be the direction of increasing theta as the particle is traveling. Okay, then I'm going to have the unit vectors in the ij coordinate frame or the Cartesian coordinate frame, which is fairly easy. This is going to be my unit vector I, and this is going to be my unit vector j. Okay, and I can say that if theta is the angle between the horizontal and the radial line, then that's going to be the same as this angle here. So this is also going to be theta. And lastly, I'm going to have the normal tangential coordinate frame unit vectors, which is easy now that I have the center of the osculating circle, right? So that's going to be the direction of the normal unit vector, which I'm going to call as e suffix n. And then the tangential unit vector, which I'm going to be drawing this way. Okay, and so that is going to be e suffix t. Okay, so those are the unit vectors. Then further, I'm going to say, okay, the position of this particle in the xy coordinate frame. If I drop a perpendicular down, and I'll bring this and complete this right angle triangle here. So this, I'm going to call this height as y of t, and then this entire distance here as x of t. Okay, it's of course a right angle triangle, as you can see. All right, and r of t, the magnitude of r of t is going to be given simply as r of t. All right, now what I'm going to do is in each of the coordinate frames, I'm going to start looking at the different quantities. Okay, the different kinematic quantities. Let's start with the Cartesian frame. Okay, so in the Cartesian frame, I'm going to start off with the simplest of the lot, which is the position vector. Okay, so I'm going to say, okay, hey, r of t, as you can see, is x of t in the I direction, y of t in the j direction. Okay, so this is going to be xi and then yj. How about the velocity? Velocity is going to be dr by dt by definition. So this is going to be the time derivative of x, time derivative of y, which can be specified as vx and then vy. Acceleration is going to be dv by dt, which means time derivative of x dot, which is x double dot, and then time derivative of y dot, which is y double dot, okay, in the j direction. This can be also written as vx dot and vy dot, because I'm differentiating the x and the y components of the acceleration, or this is eventually axi and ayj. And if you want, you can also write the position vector as rx in the I direction, ry in the j direction. Not necessary, just more confusion, but as you can see, that's the situation, okay. And it's very obvious to see that, okay, vx is x dot, vy is y dot, and so on. I'm not going to go through that. Second thing is I'm going to look at the normal tangential coordinate frame. Okay, in the normal tangential frame, we start off with the velocity vector. Okay, let's say v of t is going to be magnitude times its unit vector. That is as simple as it gets. Acceleration, as you know, is dv by dt by definition. So this is going to be v dot and v squared by rho en, and this is the same as at et an en. Rho is the radius of curvature at that point on the trajectory. So in this case for us, this distance here, you can call it as the distance rho. Okay, so that's the distance rho. All right, and so I'll write that out here. So rho is the radius of the osculating circle. All right. If I need the position vector in the normal tangential frame, what I have to do is I have to perform a coordinate transformation. Okay, so to obtain position vector, in the normal tangential frame, you will see that we will have to employ a coordinate transformation. Okay, so we have to perform coordinate transformation from if depending on the problem. I mean, for example, maybe if I know the angle between ET and I, or ET and J, then I can perform a coordinate transformation, take the position vector from the Cartesian frame onto the normal tangential frame. Okay, so coordinate transformation depending on the information given. Okay, so this is depending on information given, and this is something that I'll be specifying in a separate lecture. So how to perform coordinate transformations and so on. Okay, then I go to the radial transverse unit vector system. Radial transverse frame, and what are the things that we have in the radial transverse frame? Okay, so we start off with the position vector. R of t is just magnitude times the direction. Okay, then velocity vector by definition is dr by dt. So this is going to be r dot er r theta dot e theta, which can be written as vr er and then v theta e theta. Okay, and then likewise your acceleration vector, which is dv by dt, is r double dot minus r theta dot square er 2 r dot theta dot r theta double dot e theta, which is the same as v dot r er and we are E dot of r v dot theta E theta plus v theta E dot of theta. Okay, that's the typical way that you obtain it, and this entire term here we will call it as the radial component of the acceleration, and this is going to be the transverse component of the acceleration. Okay, so this is the basic summary of all of these, and couple more things that I want to do is the following. So here is an important thing. Okay, so okay, my important did not come out too well, so maybe let me rewrite it again. Okay, if you have suggestions on how to write on this device, I'll be more than happy to listen to you on that. All right, so the important thing is this: a vector is a vector is a vector. Okay, a vector is a vector is a vector. What does this mean? This means the following. Okay, I can say that r of t, which is xi yj, is the same r of t in the radial transverse or the normal tangential frame. Okay, which tells me that r, the magnitude, is x square plus y square whole to the power 1 by 2. Okay, that's fairly useful to me. Okay, useful to know. Then the second thing I know, okay, I can do the same thing with velocity. So v of t, which is x dot I y dot j, which is the same as v et, which should be the same as r dot er r theta dot e theta, which tells me that okay, hey, v is x dot square y dot square whole to the power 1 by 2. This is the same as r dot square r theta dot whole square to the power 1 by 2. Okay, the magnitudes are equal, the vectors are equal to each other, so that's essentially the story. And then I come to the big guy, which is acceleration a of t, which is x double dot I y double dot j. This is the same as v dot et v squared by rho en, which should be the same as r double dot r theta dot square er 2r dot theta dot r theta double dot e theta. Okay, which tells me that acceleration magnitude, which is x double dot square y double dot square to the power 1 by 2, this is the same as v dot square v squared by rho whole square to the power 1 by 2, and it's the same as r double dot r theta dot square 2r dot theta dot r theta double dot whole square to the power 1 by 2. Pretty nice and powerful and useful things. Okay, so vector is a vector is a vector, which means that no matter what coordinate frame you're sitting on and looking at it, the vector is going to be the same thing. It's just that it will be looked at by a different perspective. Okay, and the couple of other things that I want to make a note of is, okay, the Cartesian frame is a fixed frame. Okay, this is a fixed frame. Which means that it is a path independent. Okay, the normal tangential frame is a moving frame. As you can see, right, different points on the path, the ET and EN directions are going to change. Okay, so this is a moving frame. Which means that this is path dependent. Okay, Okay, and lastly, the same thing holds for the normal radial transverse as well. I mean, if you look at it, different points on the trajectory will have different ER and E theta. Okay, so I'm just going to scoot over and copy this creature here and then paste it on the radial transverse as well. So that's also a fairly important piece of information. Okay, so these are all the path dependent, and then those are the path independent. Okay, so path dependence versus path independence, that's something that you want to really keep in mind, especially when you're traveling, when you're doing dynamics problems. The fundamental question is, okay, which frame should I start attempting this problem in? Do I do it in Cartesian, normal, tangential, or radial transverse? All the frames should give you eventually the same answer in terms of magnitudes and so on, but some are easier than the others, and that's the whole art of being a good dynamicist. Okay, so very last thing I want to do is I want to consider like motion along a circular trajectory. Okay, I want to consider motion along a circular path and then just draw the unit vector systems. Okay, so here I can start off by first of all drawing the circular path. That is easy to do. It's easy to draw circles, right? Okay, then let's say that, okay, this is the center of the path, and let's say the particle is traveling in the direction that my arrows are pointing. Okay, it's traveling in the counter direction. Set up a coordinate of a fixed observer first of all. Okay, x direction and y direction. Okay, then let's say that the particle is at some point in time here. Now I'm going to start by drawing the radial and transverse unit vectors. So first of all, position vector, I got to draw the position vector. Okay, so this is the position vector from the observer's location all the way to there. So that's going to be r of t. Okay, then I'm going to draw the radial transverse direction. You'll see that the radial direction is just pointing right out of there, and then the transverse direction is going to be in this manner. Okay, I'm sorry, E theta. You'll soon see that that's also the same as E theta, ET. I just went ahead of myself. Then I'm going to have the normal and tangential direction. So the normal direction is going to be pointing towards the center of the path, right? As you know, if you have a circular path, the osculating circle is the same radius at all points. The tangential direction is going to be pointed this way. Okay, so this is going to be ET. And of course, you can have the I and the J coordinates set up there at the same point, or I can just draw it down here. This is going to be the unit vector I and the unit vector J. Okay, does not matter where you draw it, it's pretty much the same thing. Alright, so the moral of the story here is the following. If you have a circular path, E theta and ET are coincident. Okay, so here you can notice that ET and E theta are coincident, and ER and EN are along the same line. Coincident as well, but they are in the opposite direction in this case. Okay, so if you have such a situation, right, then if I say that the radius of the path is some value rho, let's say is rho. Okay, if the radius of the path is rho, then we obviously know that, okay, at any point the position vector is always equal to the same magnitude rho. Okay, so which tells me that r of t is going to be rho times er, which tells me that r is rho, or the length or magnitude of the position vector is a constant. Okay, which tells me the following. Okay, if I look at v this is v et, right? But v is also r dot er plus r theta dot e theta, right? But then if r is equal to rho is a constant, then this tells me that r dot is equal to 0, r double dot is also equal to 0, okay, which essentially tells me that, okay, hey, v is nothing but r, which is rho times theta dot e theta, which means if I do the comparison, I end up getting v is equal to rho times theta dot, or you would have known this as v is equal to r times omega, where omega or theta dot is the angular velocity along the path. Okay, so here omega is equal to theta dot is the angular rate, and then r is equal to rho is the radius of the path. Interesting, right? This is the result that you might have known from before. Okay, this is of the same form. And then let me also look at the acceleration. Okay, so from the acceleration perspective, so this is one thing. Okay, this is one thing, then this is the second thing. Okay, then from the third perspective, if I look at acceleration, this is v dot et plus v squared by rho en, okay, which I can write as the following. Okay, so this is going to be v dot et, and then this is v square by rho is the same as what we have. So I guess I don't have any changes to do here, so maybe I don't even need to do that. Let me maybe go on to the radial transverse thing. I was thinking of doing something here, but no, probably not. Okay, but in the radial transverse, which also tells me that in the radial transverse system, a, which is r double dot minus r theta dot square er 2 r dot theta dot r theta double dot e theta, right? Now I can cancel off a few of these terms. This r double dot is gone, terms containing r dot is also gone. Okay, this is mostly because of the fact that r dot and r double dot are both equal to 0, right? So because of this particular fact, I'm going to bring that down here too. Okay, this is because r is a constant. And so if I clean up my act here and then say, okay, a is now going to be minus r theta dot square, but instead of r I can write it as a rho, so that's going to be minus a rho theta dot square er, and then I'm going to have a rho times theta double dot e theta. Okay, this is the acceleration in the radial transverse frame, and it is very obvious for me to see that, okay, hey, if I have v, so we know that v is equal to rho times theta dot, right? That is from this one here, okay, from the velocity expressions, which means that if I do the differentiation of v dot is going to be a rho dot theta dot plus a rho theta double dot, right? That's the first thing. But then rho dot is 0 because rho is a constant, so this term is knocked off, which essentially tells me that, hey, v dot is the same as rho theta double dot, which is what I'm seeing here. It is very obvious that e theta and et are in the same direction, right, as you can see. So that's why I'm getting the same acceleration in that particular direction, okay, which is the same as v dot. Okay, and then I can also say, okay, rho times theta dot square is essentially, you know, I can write it in the following manner. How to manipulate this? So we have v is equal to rho times theta dot, right, which means that if I want to write this, then if I say it's v square by rho, then that's going to be rho theta dot whole square divided by rho, which is nothing but rho times theta dot square. Okay, which tells me, so v dot is the same as rho theta double dot, and v squared by rho is the same as rho theta dot square, which tells me that acceleration A is, if I bring back minus rho theta dot square ER, that's going to be minus v squared by rho ER, and then I'm going to have v dot E theta, okay, which essentially tells me, so this shows that ER is opposite to EN, and ET is parallel to E theta, okay, is parallel and coincident with E theta, okay, or this can essentially be written as minus v squared by rho in the minus En direction plus v dot Et. Okay, this is because ER is opposite to En. Okay, and so if I do this manipulation, then I get the same acceleration as in the normal tangential coordinate frame. Alright, so this was a fairly comprehensive summary of all these relationships. This is a special case, okay, special case of motion. Let me write that color, correct? Okay, so with this special case of motion, then you can see that we can perform manipulations, and we can just express the velocities, accelerations in different coordinate frames. All right. Okay, thank you very much for your patience, and I'll see you in the next talk. Bye bye.